Welcome to Module 4 on differential power analysis and how we can use differential power analysis to break cryptographic implementations on embedded systems. So my name is Colin O'Flynn, and I'm going to take you through how we can use the ChipWhisperer software to run various attacks. In this case, we're going to look at a AES implementation, AES written in C in this case, running on some different types of target devices. We can do this attack with the ChipWhisperer Lite or the ChipWhisperer Nano. Both of these will work to follow along almost exactly. You can also use stuff like the ChipWhisperer Pro as well. But yeah, with that in mind, let's take a look at what we're doing. So I want to talk a little bit about the theory first. So what we're talking about is devices where, there's some hardware module with encryption inside it. And when we say hardware module, this can mean like a peripheral on a microcontroller. And this peripheral could do stuff like be decrypting SPI flash. And in which case this would be called a decryption module. But the same sort of attack is going to apply. And it could be too, that this decryption module is taking in data from some serial line and decrypting it. Now this module can be hardware or firmware. So these attacks work on both hardware and firmware. So you don't have to really know the difference between what happens if we talk about software versus what happens if we talk about like a hardware accelerator. And what you've got is you have, for example, inside an IC that's implementing an encryption algorithm. You have a bunch of data buses inside this IC, and these data buses are going to move data from, maybe a main memory into an ALU or something like that. So somewhere inside this chip, we have data that's actually moving across a bus. And if you look at these data buses, you can consider them like wires. So this could be, say, like a data bus bit, right? And this single bit is effectively being set to a high or low voltage. So the voltage on that data bus bit is changing between, like if a 1 is being transmitted or a 0. And this is internal to the chip itself. So inside the chip, you actually have a data bus that's transferring the data around on the chip. And this is very similar to like a capacitor, because with a capacitor, we have a charge, right, being put on something. And this charge is compared to a reference plane, and this is like the ground in our case. So what we have is a data bus bit, so data bus bit, and we have like a ground plane, right? So this is roughly the exact same situation that lets us generate a capacitor. And what do we know? We know that charging and discharging a capacitor actually takes a small amount of power. So if you can imagine your data line transferring from 0 to 1, this is it going from the uncharged to the charged state. And if you imagine that transition, so let's also imagine that there's a state over here where these other three did not change. At this point in time, there's actually going to be kind of a spike, right, on a power consumption graph. So what we have is that it actually takes a small amount of power to transition a single bit from 0 to 1. Now, the interesting thing is what happens if we transition, say, like multiple bits, and this is something we'll look at with something called correlation power analysis. What if we transition multiple bits from 0 to 1? We actually see some relationship between the number of bits that change and the power that's consumed. But we're not actually going to worry about that initially. All we're really going to look at first is what happens if a single data bit changes from 0 to 1. And how can we detect this change and use this to actually exploit a system? So we're going to go back to our microcontroller. Our microcontroller is running crypto inside it, like we said before. And what we're going to do is we're going to set up a pretty basic attack system here. And we're going to set up an attack system like this, where we have a microcontroller. So we have a microcontroller. This is the power to the microcontroller. And we're actually going to measure the power going into the microcontroller. So we have this shunt resistor here, right? And if you remember some basic electronics, what you have is that a power consumption, the voltage across the shunt resistor is going to be related to the current through it. So we now have a voltage here is related to the power consumption, because that's what we're ultimately trying to measure, is what is the power consumption of the microcontroller, because we think the power consumption is going to be related to data. And the final thing we're going to do is we're going to somehow connect the microcontroller to a computer such that the computer can both acquire power measurements and instruct the device to encrypt or decrypt data. So we have this situation where we have a device that we can encrypt or decrypt data, whatever it might be. And we have a computer that's actually controlling that. So with the computer controlling it, we're able to generate a power trace of the device as it's performing a specific encryption. So this is really handy for us because we're basically going to end up with this big table. And we're going to assume, like let's say it's a very basic device we're attacking, where for every byte that we send to it, it just uses a single byte and we generate a single power trace. So this is a measured power trace, right? And this is the data in use. And the data in use is not a secret, because this would be, for example, like if we were decrypting something, the data in use would be like the file that's being decrypted. So we don't have a big worry about actually being able to control that. The final thing we need is we need to have an idea of what the device is doing. So for this attack to work, we don't need the actual implementation specific details, but we need like a rough idea of what the crypto system is implementing. So in this case, we're going to talk about implementation of AES. So we're running AES in this thing. And what we have is we have this idea that, if you use AES, it always looks something like this. So we have the input data, for example. So if we talk about encryption, we have the input data up here. As the first part of AES, this gets XOR with the key. So we have a byte of the key. So we're just going to consider a single byte right now. The byte of the input data is XORed with a byte of the key. It goes through this lookup table, and then it goes onward in the algorithm. We don't care about the rest of it. All we care about is that this initial step is actually done. So basically what you have now is you have this input data that we know, and we have this key that's a secret that we don't know, that we want to recover. And over here, we know that it XORs, and then it goes through this lookup table, which is called the AES substitution box, or S box. And how we actually do the attack is we simply take our input data and we split it we're going to end up splitting it into two groups. And it's pretty straightforward to do this, because what's going to happen is we'll take our input data and we'll guess what the key is. So we have no idea what the key is, but we're going to say, what if the key was 0? Well, if the key was 0, what we would have is, we would have, for example, the input data would be XORed with 0. The XOR output would be C7. If you look up in this little lookup table, what C7 is, that's C6. So we'd have C6. And all we're going to do is we're going to look at the lowest most bit of C6, right? So 6 is 110, 0110. Right? And the lowest most bit is 0. And we're going to do that for every single one of these. So we basically guess what the key is. And in this case, it's a tractable guess, right? We only have the 256 possible guesses. So we're looking at a single byte of the key at a time. This is the really important thing with DPA. It's a single byte of the key that we're actually recovering from this. And so if we did this for every possible key, we're going to end up with tables like this that basically say, you know, is that lowest most bit 1 or is it 0? And the way the attack works is we're simply going to group these. We're going to say, well, if the key was FF, you know, I'm going to take all my power traces and I'm going to group them together. And I'm going to group them into cases where the key is 0 and where the key is 1, key bit is 0, key bit is 1. And we're going to use differential power analysis to figure out if this is true or not. So the trick here, where it gets interesting, is we're going to use DPA to actually figure out if our guess was correct or if our guess was incorrect. If it's incorrect, the idea is that the power trace distribution is going to look it's going to be random, so we'll see no big spike. If we were correct, what we expect is that if you look way back, right, to where we started talking about this idea that there's going to be a big power spike, we're basically going to exploit that. We're going to exploit the idea there should be some power spike related to, you know, the state of a transition or the state of an actual, in this case, the value of the bit on the data bus itself. And this should give us what the correct encryption byte is, or the most likely byte for the key. The nice thing about this attack is that we apply this attack individually. So even if we're looking at AES 128, which we'll do in a moment here, it's applied a single byte at a time, as you can see here. So that's kind of the trick with this whole thing. So with that, we can actually take a look at how you do this with the ChipWhisperer. So what we're going to do now is we're going to take a look at some ChipWhisperer hardware, because what we need to do is we need to actually, implement this attack. So there's a few different things we could use here. There's two possible boards that we have set up. There's other ChipWhisperer hardware too we won't talk about. There's the ChipWhisperer Lite, which is the larger of the two boards, and the ChipWhisperer Nano, which is a smaller of the two options. And both of them can do the attack. And they both have a kind of similar architecture, so we'll sort of take a look at how they work. And you'll notice that both of them have sort of a split. So if we stack them up beside each other here, you'll notice that they both have sort of this split section. And what this is that the ChipWhisperer single board solutions have this idea of a built-in target. So this side here is the target. We're actually going to be attacking a implementation that's on this target here. For the ChipWhisperer Nano, the implementation we're loading is on this section here. So we have two different targets. They're both STM32F devices in this case. This is an STM32F3. This is an STM32F0. And on the left side is our power capture hardware. So it's different between the Nano and the Lite. So quickly I'll talk about the Nano first. The Nano has a more basic architecture. What you have is a small op-amp with a fixed gain, an ADC, an 8-bit ADC, and it's clocked into this microcontroller, which then lets us download the traces over USB. We can also program the target through this, so we're going to change the firmware. We're going to build our own firmware that we program this onto. The ChipWhisperer system uses something we call synchronous sampling. So this means that this device is actually clocked from a derivative of this clock. So we guarantee the cycle accuracy of all the clocks. So everything's done in lockstep. So we have one cycle of the target clock. We get a specific number of samples of the power. So this is very handy because we can get to know what power is related to what's actually happening on the device. The ChipWhisperer Lite, so if we take a look at the ChipWhisperer Lite architecture, it's similar. Again, we have a target section here. We have a much nicer amplifier here. So this is a low noise amplifier. And we can zoom in a little bit here. so you can see this stuff better. It's AC coupled, so the input is always AC coupled on the ChipWhisperer Lite, and the same on the Nano. We do this because all you really care about is small variations in the power. We don't care about absolute. We care about small variations in the power, so that's why we're using AC coupling here. What we also have is a ADC up here. So this is a 10-bit ADC as opposed to the 8-bit ADC on the Nano. And it can run up to 105 megasamples per second on the Lite. So the Lite's ADC is clocked via an FPGA. So this is the major difference between the Lite and Nano. This thing has an FPGA on it, so we can do a lot of pretty nice triggering and other work on the ChipWhisperer Lite. So we can do stuff like, trigger, delay a bunch of cycles, and then record that data to a buffer and download it to the computer. The ChipWhisperer Lite, I should mention, also can do clock glitching, something that's not possible on the Nano. With the FPGA on the Lite, we can do a lot more fancy things like that. But the basic idea is exactly the same. When we go to use it, we're either going to plug in like there, or we're going to plug in just like this, right? So whichever you're using, all you've got to do is plug in to the device, and you're kind of good to go. So I'm going to use the ChipWhisperer Lite, and you just need to remember that in the next little section here. All right, so we're going to use something called Jupyter Notebooks. If we didn't have this running, we'll have a virtual machine. So this virtual machine, we don't actually need to use at all for anything. Even though it's running here, I don't have to log in or anything like that. It's basically communicating to the ChipWhisperer, so I can actually check that ChipWhisperer Lite is connected to it. There should be a ChipWhisperer Lite. Normally we would get a checkbox here, but we're just going to keep continue onward. So this actually, and I'll close this page here to show you from fresh. We actually have this Jupyter Notebook is basically this little web interface thing. So this is pretty cool because we're going to do all sorts of interactive work. So this is actually running on this little backend server. It's serving this website here, and we access it on localhost 8888. So if you don't have that up, you'll have to go to the localhost 8888, and then you'll see this thing here. So this is where we get. And these are all the tutorials we can run. So there's a whole bunch of tutorials. Some of them are not for, some of them need specific hardware. So there's stuff like boards that work on the 305, so the RTX boards. There's targets that work on the Pro, but a huge number of them you can do on the Lite and a lot of them on the Nano. So we're just going to look for AES DPA 3 or PA DPA 3 AES DPA attack. So if you find this guy, you can just click on it to open it, and you should get something like this. So this is interactive Python as well as Markdown and stuff like that. So if you double click on a cell, you'll notice it actually lets me edit it. And if I run it, in this case, it's just documentation, so it just goes back to visible. But we actually have various Python that we can run interactively. So you can see, if you go back, you'll see various introductions to it. But I'll just run through this pretty quickly. So this talks about the things in the tutorial, about how it works, and that's what we're going to do. The important thing here is there's a platform. So you'll see it says CW Lite ARM. If you're using the Nano, you'll have to change that to CW Nano, but I'm going to use the CW Lite ARM, so I'll leave that alone. And we'll just run each of these in sequence. So how am I running this? I'm either hitting Shift Enter, or I go up here and hit Run. And each one runs and gives me any output. So for example, this block here is actually building firmware and showing me the output of that build process. So what we need to do next is we actually need to get our power traces. So to do that, I'm going to run these scripts that connect to the ChipWhisperer Lite and program the device here. Hopefully that works. If you get some error, so as a note, like if I go ahead and unplug the ChipWhisperer, let's see what errors you get. So if we unplug it, and if you go back and try to run some of these, you might get different errors. So if I try to run this, you'll see I get a no such device error. So this just tells you, I need to fix something. So in that case, you might try, like, let's plug this back in and run this. But this still might give you an error. So I've tripped an error where I reconnected but the device doesn't know. You'll want to use this button up here in the top, this restart the kernel. What this button does is this just clears everything away. So, if I get an error, it just clears it all away. I've got to go back here and start. So you need to go back and restart all of the cells for this to work. So I'm going to unplug, replug, and then run all the cells, and we'll check if this works. Okay, so it worked okay, no error there. We can continue onward. So the final thing I'm going to do here is going to generate this real-time plot. And this is just going to let me do some real-time graphing as I capture the power traces. So there's a very basic loop in here that's going to run. And it's going to capture a number of power traces. In this case, it's, for differential power analysis, we may need a lot more power traces. But this is actually the code running on the device itself here. So we can see this code running here. And on the ChipWhisperer itself, it's going to look something like this. So it'll look a little different for each one. But you can see there's, a quick capture light as it captures, and then some other status lights that are blinking. So one of them is as the device is armed, we'll see some lights blinking. And this light down here is just a general status light. So we'll let that guy run and come back to it once it's complete. So we know it's complete when, here it gives you a bit of a countdown. So it'll take a few minutes to capture enough traces, but we should be able to get a successful attack at the end of this. Once this completes here, we can continue on with the rest of the lab. So we have enough traces. What we'll do is we'll basically go through that guess and check. So we saw in the slides, there's this guess and check idea where it's going to iterate through every possible byte, run it through a model, and try to separate possible values of the key and the resulting power traces into two groups, and then compare these two groups. So that's exactly what we're going to do here. So to do this, we build a model of our encryption, which is literally just the beginning part of AES. And then we're going to separate them into two groups of traces. So we're going to separate them into groups of traces where we have a 1 and we have a 0. So this chunk of code here just does a basic separation based on a bit being set to 1 or a bit being set to 0. And what this loop is doing, so I'll just run this loop again using the run button here. It's going to try every key guess. So you can see it's iterating through every single potential key guess. And for every of these key guesses, it's separating it into a group of traces that's a 1 and a group of traces that's a 0. And eventually, we'll get a look at what that looks like. So we can see it's telling us what it guessed the encryption key was. And here it's printing what the actual encryption key was for each byte. So it can go through every single byte and do each of these operations in a time. And if that works, we should get this to work for every byte in a row. So you can see it'll take a little bit of time to go through. But once you get one or two working, you get the idea that this is working pretty well. So let's see, the second one works. So I'm going to stop that. Because what we can also do is we can plot some of these differences, and so I only have the first 2 bytes working, but we can take a look at how strong the differences were at the point in time the actual key was in use. So we can see this is the difference between, for the correct value, where the bit was 1 and where the bit was 0, and we can see this huge spike in power consumption. So this spike is going to vary depending on how many traces. If I didn't take as many traces or I had a noisier system, I won't get as nice a spike. And the red one's for a different byte trace that we tried. So there's some differences we can play with here. We can even go through and play with, different incorrect and correct traces and stuff like that. But the basic idea is just to see how differential power analysis is actually able to break these devices in real life. So differential power analysis isn't the most powerful attack we'd commonly use. There's another attack, correlation power analysis, that's much, much faster. You can run correlation power analysis in, like a minute or less often for these simple devices. But differential power analysis can be a little easier to understand and to actually go through how everything works. So you can experiment a little more with that. And if you get, this working, then also give a shot to some of the other tutorials in here. And if you need a bit of a hint, there's this suggested completion order that talks about some of the other stuff you can do. And some of these earlier tutorials will go through various types of attacks as well that you can do in this thing. But this is kind of a little example of how you can use either the ChipWhisperer ARM or the ChipWhisperer Nano to run various side channel power analysis demos and see for yourself how embedded devices can be broken with advanced attacks.